Okay, this question's all about polar molecules. So usually the easiest thing to do with all of these is to draw them. So for A, it's just CH4. Now all of these are non-polar bonds. The difference in electronegativity between carbon and hydrogen is less than 0.5, so they would be seen as non-polar. So there's no dipole across them, so it cannot be A on this question. C2H4, we know from earlier on, or later on actually, in our topics, we have an alkene. This is also non-polar. None of those bonds are polar because there's no big difference in electronegativity between carbon and hydrogen. It's less than a half, so therefore it's non-polar. So this molecule is also non-polar. C, you have a carbon, 3 hydrogens, and then a chlorine. Now, the difference in electronegativity between the carbons and the hydrogens is the same as it was in A and B. There's no difference, but now you have a delta negative chlorine and a delta positive carbon because the chlorine is more electronegative than carbon. Now, because you therefore have a difference across the molecule where you have a slightly more negative side of the molecule and a slightly more positive side of the molecule, you now have a polar molecule. So C has to be polar. D, just to check, you've got a carbon and it's surrounded, equally spaced all the way around, is 4 chlorines. So although all of these chlorines are delta negative, because they are evenly spaced all around the molecule, so if we drew the 3D structure, for example, over on the left here, we would have a totally symmetrical compound with negative stuff all the way around the outside, or delta negative stuff all the way around the outside, and the delta positive stuff in the middle. So there's no difference across the molecule, so therefore that is non-polar, even though it contains polar bonds. Okay, and then the next question, which of these is a polar molecule? Well, if we start with A is oxygen connected to 2 chlorines, and we know that oxygen has got lone pairs of electrons. Now, you need to check your electronegativity values if you want to see kind of which way the bond is polar. Is it polar at the, is it more negative at the oxygen end, or is it more negative at the chlorine end? Okay, so oxygen is, we can actually write these values down. Oxygen is 3.44 and chlorine is 3.16. So actually, oxygen's more electronegative and chlorine is electropositive. Now, because that lone pair of electrons is pushing, or those 2 lone pairs of electrons are pushing the chlorines away, we have a difference across this molecule. So we have negative at one side of the molecule and positive at the other side of the molecule. So A is our polar molecule. Okay, we can just kind of check in with B. B is boron trichloride, and they are all evenly spaced around. This is one of those compounds that doesn't fit the octet rule. Okay, it's similar to BF3 on page 89, so you could take a look at that. Okay, now even though our chlorines are delta negative compared to our boron, because they're all evenly spaced around the molecule, and there's a line of symmetry within there, or 3 lines of symmetry, 4 I think, then there's no difference across the molecule, so therefore this is non-polar. C, you saw that in the on the previous slide. Okay, so C is the same as no difference across, and then S looks very complicated. D looks very complicated. SCl6. So you have all of these chlorines coming out. This is an octahedral. It's an example of our fancy shape. An octahedral. It's, if you want to check those out, they're on page 92. And the difference is chlorine is more electronegative, so there's a slight difference, so it's more negative. But because again these are all spaced out all the way around, evenly all the way around the sulfur, with sulfur being delta positive, there's only difference across the molecule. The whole outside is negative and the inside is delta positive, so therefore it's non-polar. There's no difference across the molecule. There we go. Hopefully that's been helpful.